if I remember, last time our end was with this part which is connected with detectors, and if you remember, we discussed detectors which is possible to use for detection of gamma radiation, and if you remember, it was mostly two types of detectors. One type was semiconductor detectors, and in this case, mostly used detectors are germanium detectors and even high purity germanium detectors. And second type of detectors, which are often used for detection of gamma, are scintillator detectors. Scintillator detectors, and in the case of gammas, the best scintillation detectors are anorganic detectors. That means, if you remember, we discussed this dependency of cross-section of photo effect, Compton scattering, and pair production on atomic number of this material, and for photo effect this is Z in 5, yeah, for Compton scattering and for pair production it is linear, but in any case for high Z this cross section is much higher than for a small z. That means organic materials are not fine because you have only hydrogen and carbon, which are relatively very light atoms. Yeah, that means we have this two types of scintillators of detectors. One, they are anorganic scintillator as barium fluoride, BGO, PbVO4, and another anorganic type of scintillators. And second, there are these semiconductor detectors. And which is main difference between these two? For semiconductor detectors, we have much better energy resolution. For scintillation scintillators, you have much higher efficiency, but much worse energy resolution. Okay, this is the reason why it is fine to have sometimes systems of such detectors and to produce some complex of these detectors to obtain better results and better spectra. This is the reason why we have these detector systems, and we will discuss different type of these detector systems. One is anti-Compton spectrometers, pair spectrometers, and okay, also sometimes it's fine to have much complex systems which are based on a system of this scintillation detectors, and it's possible to obtain crystal spheres, walls, complex setups of this semiconductor and scintillation detectors, because for some experiments which is necessary to do in particle and nuclear physics, we need to have 4 pi acceptance, and it is necessary to have complete coverage of acceptance of angle in such experiments. This is for nuclear physics and for research in this region. For application, there are chambers which are given by many of scintillation detectors, and one of this is PET chambers, that means positron emission tomography chambers, but I will say you later what is and why they are used. Okay, how it looks like this anti-Compton spectrometer. This is a spectrometer in which we have these germanium detectors, these semiconductor detectors, which is surrounded by scintillation detector. Mostly it is, for example, natrium iodide or BGO. And as I said, this germanium detector has very high energy resolution. That means nice energy resolution. Scintillation detectors have high detection efficiency of Compton scattered photons. It is given also by this because if gamma is scattered by Compton scattering, energy of this scattered photon will be smaller than energy of this primary photon. That means also because dependency of cross section of this Compton scattering and also a photo effect is very quickly decreasing with energy. That means if energy will be lower, that means this cross section of photo effect will be much higher and probability of detection of this Compton scattered photon will be much better. That means if we have anti-coincidence between this semiconductor detector and scintillation detector, it will be possible suppressed this Compton scattered photons, and we will have strong suppression of Compton background, and also this escape peaks up to, and this suppression will be up to 1 order. Yeah. As I said, photons after scattering have lower energies. That means higher probability of photo effect. That means, okay, this is very big, high probability to detect this scattered photons. What is also useful, if you will have some asymmetric position of this semiconductor detector inside this natrium iodide or BGO detector. This is advantage. Here it's possible to see which will be probability of detection of this scattered photon because here you have smaller energies after scattering. That means it will be necessary this thickness to be smaller than in this direction, because in this direction you have higher energy and smaller probability of detection. Yeah, that means, okay, you have here, and this our BGO crystal is around here. That means here is this thickness of this scintillation detectors much higher than in this direction. But okay, this asymmetry is perfect because that means that in all direction you have the same probability that this scattered photon will be detected. Yeah? And after anti-coincidence, it's possible to suppress this Compton background, and you will obtain better spectra. Okay, here is some example of such high purity germanium detectors, which is inside this anti-Compton shielding, and okay, that possible to have better spectra. And you see also this low energy weak lines on the background, Compton background of strong lines with higher energy. Okay, the same type of detector, the same combination of semiconductor detector and scintillators, it's possible to use also as pair spectrometer. In this case, we are checking coincidence between this gamma detected in this semiconductor detector and two gammas which will have 511 kV as scintillator. In this case, this is such process. You have pair production in this semiconductor detector and two produced photons with energy 511 kV, yeah, which both are running in opposite direction. That means these two are running in opposite direction to scintillator. That means if you have cut of this scintillator to two halves, it's possible to detect both of this and identify both of these gamma photons with energy 511 kV. Yeah, that means it's possible, and if you will make coincidence, yeah, and you will check only these events, it's possible to suppress all of another events. Yeah, only these are possible to see, and this is very strong background suppression, and it's possible to see only line with this pair production. And okay, that means that it is necessary to be higher energy gamma photons, gamma lines. That this is for detection of high energy gamma. And because it's necessary to have enough energy to have possibility to produce this electron-positron pair. Last possibility for usage of such combination of detectors is summation detector. Again, this is the same combination, and we will make one thing. We will sum energy which will be detected in semiconductor detector and this scintillation detectors. This is fine from this reason. Part which is detected in semiconductor detector has very nice energy resolution. That means energy is derived nicely. This part which is detected in scintillation detectors, because this is very often for high energy photon, that you will have Compton scattering or this pair production. That means after Compton scattering, some part of energy is going to these scintillation detectors. Determination of this energy is worse than in semiconductor detector, but if you have part of your energy derived with nice resolution, some smaller part with smaller resolution, but you will have very nice efficiency, because scintillation detector has very good efficiency, and it is very big probability that this Compton scattered photon will be detected in this scintillation detectors. That means resolution is energy resolution is worse, but this worsening is very small. It is not dramatic, but you have dramatic increasing of efficiency. That means it's possible to use you will obtain this full absorption peak without marked downgrade of energy resolution, but with very nice efficiency and increasing resolution, energy resolution. Yeah. Okay, that means it's possible for spectrometer, which consisted of this semiconductor detector with this high purity germanium detector surrounded by scintillation detector. This spectrometer can work at anti-Compton pair and summation modes. That means, and together, it's possible to obtain all possible spectra, this anti-coincidence, coincidence spectra, and it's possible to analyze later as anti-Compton spectrometer, pair spectrometer, and also summation spectrometer. I said to you that for nuclear structure studies, we sometimes need to have full 4-pi acceptance. Yeah? That means it's necessary to detect all gammas which are produced by some phenomena. Yeah? This is very important for studies of very rare processes or high energies of nuclear excitation, because there are high cascades, long cascades, and many gammas which are emitted. That means you need to have a very big number of these detectors. Yeah? It is nice for analysis and study of super deformed states, giant resonances, exotic nuclei. Yeah, and they started in 80s. They started to have enough, or this electronics and also this detector starts to be cheap, and it was possible for laboratories to have many of such detectors. Yeah, and at the 80s, as I said, they produced first generation of such systems. Yeah, in these systems, it was about from 6 up to 20 semiconductor detectors with anti-Compton shielding and set of different scintillation detectors, combination of semiconductor and scintillation detectors. Some examples of such systems, there are this TESA 3, Chateau de Cristal, Osiris, Nordball. And it was necessary from this point of view because, for example, this super deformed band states, they have only about 1% of full intensity of this gamma decays. And they had about 20 transitions in one cascade. Yeah. Second generation of such system of detectors, they started at 90s, and they started to be modular, flexible, and they were also even nomad setups which work on more accelerators. And what was important? It was nice efficiency of this. This ratio between peak Compton, which was given by this anti-Compton shielding and suppression, anti-Compton suppression of Compton background. Nice resolution. And what was also important, it was necessary to analyze also Doppler shift. Maybe I will ask you, do you know what is Doppler phenomena?
Yes, a bit.
Maybe say me. Do you know what is?
Yeah.
Okay, explain me, yeah? And where is possible to see this Doppler
I know
phenomena?
it's about frequencies and electromagnetic, but not really that much more. We can see it in medicine, but
okay, that's it is for wavelength which is changing if the source of these waves are running around us, yeah, and if it is running to us, it will be go to higher frequencies. If it is running out of us, it will be go to lower frequencies, yeah. It is firstly by Doppler, it was firstly discovered for sound, yeah, that means for these sound waves. But we know that it is also working for visible light. For example, if you have stars or galaxies, it's you know that it is redshift, which is given by movement of this star from us, or if this stars are running to us, it will be blue shift. And but it is also possible to see this Doppler shift for gamma, and how it's possible to study some the excitation of nucleus or excited state in this nuclear physics studies. In this case, it's necessary to produce excited state of nucleus, yeah? And it is possible to obtain by this that you have accelerated nucleus and you have target nucleus. By collision and merge of these two nuclei, you will obtain excited state of new nuclei, which is given by these nucleons from these two nucleus, target and projectile nucleus. Yeah, that means you will obtain compound nucleus in excited state. But because you obtain this by accelerated nucleus, it will be necessary to have movement of this compound nucleus, that this is moving against our laboratory and also against our detectors. And if you have movement, you have also some shift of energy. Yeah, that means it depends of this Doppler shift depends on a situation which is angular distribution of this detector against this movement of this nucleus. That means for detectors which are in some position, it will be Doppler shift big. It will be another position in which it will be not movement to this detector or out from this detector, it will be no Doppler shift. But in any case, it is necessary to make analysis of this, and it's necessary to analyze spectra, and in the spectra it's possible to see this influence of this Doppler shift. Yeah, that okay, this is about Doppler shift. And this usage of these semiconductor detectors with this shielding of these scintillator detectors, it's possible to obtain efficiency of such systems up to 10%. Yeah? And we have tens and hundreds of detectors in this case. Here is example of such system of detectors. This is Eurogam second, and what you see, this is this URs for this liquid nitrogen, because this semiconductor detector, this germanium detectors, it's necessary to cool on the temperature of liquid nitrogen to be for work. That means it's necessary to have this UR. Okay, there are some examples. For example, this is at the United States they had from 1995 this gamma sphere, about 70, 100 this germanium detectors with BGO shielding, and as I said, 4 pi geometry. It is for only for interest that such detectors was also presented at film Hulk. Yeah, that this is this science fiction or fantasy movie. Okay. And at Europe, that's for example at Darsberry, Heidelberg, Darmstadt, they were different systems from, again, also from 90s, Eurogam, Euroball, and others. And here there are these different systems. As for any of them, you see that the main visible part are these jewels for liquid nitrogen for cooling. Yeah. Okay, that's also possible to use this scintillation walls for high energy physics. Next lecture will be about this high energy gamma detection and how it is possible to use production of this electromagnetic cascade, electromagnetic shower. And okay, that means this scintillation walls is possible to use for detection of this electromagnetic showers. Yeah? And it's possible to use for identification and of high energy photons and determination of energy of such photons. First of them was Heidelberg Darmstadt wall, which used about 162 natrium iodide detectors, scintillators. At SLAC DAISY it was 672, again natrium iodide. This is for lower energies because this is not so atoms with so high Z. This type of detectors are named as electromagnetic calorimeters. Cleo 2 had already 8,000 cesium iodide detectors, and they used, because for these scintillation detectors, if you remember, it is necessary to have photomultiplier or these photodiodes, which were used here. And some example, I will show you also some results from this type of detector wall. This is TAPS, this is two-arm photon spectrometer, which used about 400 barium fluoride detectors. It was crystal with thickness 250 millimeters and diameter about 59 millimeters. It is here. It is possible to see how it looks like this. Yeah, and this is necessary also distinguish between this neutral particle and charged particle. Yeah? And for this, it's possible to put before this barium fluoride crystal some thin plastic detectors for identification of charged particle. It's possible because this barium fluoride has, if you remember, a very nice time resolution. Yeah, in this case, it's possible to measure time and to determine clearly time moment of detection. And from this, it's possible to use for time of flight measurement. That means to distinguish particle or to derive velocity of particle by measurement of time of flight. Okay, and also this barium fluoride is possible because it has two components of light emission. That means it's possible by pulse shape analysis to distinguish different particles. Okay, this type of detectors is possible to use for detection of photons from hundreds keV, from 1 MeV up to 10th of GeV, that which are produced directly or by decay of particles. This is decay of mesons. And it was exactly this NOMAD spectrometer which worked at GSI Darmstadt, Groningen, Caen, CERN, Mainz and Bonn. And in many laboratories used many accelerator and to study different fields of nuclear physics and particle physics. Here there are examples of different setups. There are crystals for another electromagnetic spectrometer, which is for CERN. This is for experiment ARIS at CERN. And here this electromagnetic calorimeter for this LHC experiment ALICE used crystal of lead, tungsten, and okay. And we will next lecture we will discuss this radiation length and molar radius. Yeah, and this length of this crystal were about 15 of this radiation length and about 2 centimeter radius. That is the sizes were about with these values, and whole area which was covered by this electromagnetic spectrometer were about 8 square meters. It is problem that in this case it is difficult to make this 4 pi acceptance, yeah, because these crystals are very expensive, not cheap, yeah. And in the case of this ARIS experiment, which is on this the largest accelerator in CERN, it is necessary to have optimization for very high energies of this gamma. That means it is from 0.5 GeV up to 10 JeV. I said you here should be, this is Czech word, that means it should be medical diagnostic. Okay, this is positron emission tomography chambers. Yeah, this is for application. Up to now, it was this electromagnetic calorimeters for high energy physics and for research and for nuclear and particle physics studies. Here you have for application, and in this case it is for medical purposes. Yeah, and what is positron emission tomography? In this case it's possible to obtain three-dimensional picture of patient tissue. It is based on usage of radionuclides which emits positrons. That means beta plus radioactivity. Yeah. In this case, you know, we have positrons are stopped, and they are stopped very quickly. It is about 1-2 millimeters distance. That means it will be in the place in which they were produced. And okay, after annihilation in the rest, you have two gammas which are running in the opposite direction. It is pure kinematic. That means if you have momentum 0 before annihilation, it is necessary to have momentum 0 after annihilation. That means if you have one gamma and second one gamma, they need to run in opposite direction with the same momentum. Okay, that means okay that we have these two, and you have two coordinates are given by position of these photons detected. Yeah. And third coordinate are determined by time difference between detection of this and this photon. That means this time will be different. This time difference will be different if this will be here or if it will be here. Yeah. This positron emission tomography chambers, they have about hundreds up to thousands per detectors. Yeah, and they are mostly scintillators. Yeah, they are scintillators because in this case we know which is energy of this gamma. It is 511 kV. Yeah, that we know. But we need to have very high efficiency. Because if we have high efficiency, it is necessary to put to patient small radiation. Yeah. And how is possible to put this radionuclides to special part of body? It is, for example, possible to use glucose, and this glucose, this energy for transfer of energy in the body. And for example, cancer cells have high necessity of energy. That means big part of this glucose is going to these cancer cells, and if you want to identify tumor, it's possible to use this positron emission tomography. And that also this part of body which are working, for example, also parts of brain which are working, they need higher portion of this glucose. And that means in this case, if you have this glucose with some radionuclide, that will more of radionuclide will go to these parts, and it's possible to identify and to make three-dimensional pictures of this part and tissue and or tumor, and after that it's possible to solve problems. Yeah? There are some example of usage of this spectrometry and detection of gamma for some application, in this case for medical applications. Okay, last part of this gamma detection and gamma spectrometry is spectrometry of high energy gamma rays. Yeah, that means there are photons with energy which have many mega electron volts up to GeV and higher. Yeah. In this case, we discussed during discussion about interaction of gammas and also electrons, that in this case you have gamma for high energies. The dominant process is pair production. That means you have production of two particles, charged particles, positron and electron. And after that, because this energy will be of this positron and electron should be also very high, because as I said, our gamma is with very high energy. In this case, if you have this positrons, electrons with very high energy, dominant interaction, and we will discuss this next lecture, is radiation that means radiation interaction. Yeah, that means in this case these electrons and positrons will produce Bremsstrahlung radiation, and okay, that means we will obtain by this Bremsstrahlung radiation. After this, we will have still this charged electron or positron and gamma. And again, if this energy of these positrons and electrons are very high, also energy of produced Bremsstrahlung radiation, produced Bremsstrahlung gammas will be high. And that means dominant process for this high energy gamma is production of pairs. And again, you will obtain new electron-positron pairs. That means you will have production still new and new photons, positrons, and electrons. And you will obtain something which is named as electromagnetic shower. And what we need to obtain total energy and direction and time of initial photon from properties of this electromagnetic shower. Yeah. For detection of this electromagnetic shower, it is possible to use more types of detectors. Yeah. But very useful are scintillation, these inorganic scintillation detectors, and we already discussed this BGO, barium fluoride, and this lead tungsten scintillator. Second possibility is that we will have some converter. The best is lead or tungsten, because maximal Z is for maximal cross section of this interaction of gamma. And this thickness will be small. And after that, during this pair production, you will obtain electron-positron pair. That means after this converter, it's possible to put some track detectors of electrons and positrons. It's possible to be spark chambers, silicon, some gas detectors, and okay, and it is possible to obtain track of this electron and positron, and from this track, and also energy of this, it's possible to obtain information about this gamma. Maybe, Camille, do you know how work these gas detectors?
No, I don't know.
This, for example, ionization chamber or proportional chamber?
No.
No. Okay, fine. Tomorrow, not tomorrow, but the next lecture, I will show you, yeah, how it is working, and okay, we will discuss this. Okay, fine. That means we will obtain this electromagnetic shower, and okay, that this end of this electromagnetic shower is 4 energies of these gammas and also of these positrons, electrons, which will be smaller. This E gamma is smaller than a few MeV, because in this in this region of energy, this pair production starts to be negligible. Yeah, but up to this 1 MeV, this pair production is possible, and if it is higher than this 1 MeV, it is dominant, as I said to you. Yeah. And also for this very high energy, this Bremsstrahlung radiation dominates. But if this energy is going to energies about a few MeV or near to 1 MeV, this Bremsstrahlung radiation will start to be negligible against ionization. Yeah. In this case, this very important quantity for description of this electromagnetic shower is radiation length. This is length in which a high energy electron will lose energy, and this energy will be only this. Yeah. And okay, if we have energies of this gammas which we want to detect, yeah, in this case we need to have detectors which thickness will be approximately 15 times this radiation length. That means only if you want to have development of this electromagnetic shower and this energy converted to these gammas, electrons and positrons, which will have on the end energy which will be near to 1 MeV, and that means this it will be full development of this electromagnetic shower. We need to have 15 radiation length. That means, okay, we need material with such thickness. Second very important quantity is Molière radius. This is if we have Molière radius, in this case about 90% of this shower energy is inside this radius. Yeah, that means this electromagnetic shower development inside this Molière radius. Yeah. And relation between this radiation length and this Molière radius is approximately here. Yeah, this is depending on material and on atomic number of this material. Okay, and how is possible simply described by simple model this development of this electromagnetic shower? Yeah, during whole process you have multiplication of particle. Yeah, that means by interaction of gamma you will obtain two particles. That means one electron, one positron. Yeah, that means pair production. Yeah, by emission of Bremsstrahlung radiation, you will have after that charged particle and photon against two particles. That means any process will produce two particles. Here you have, okay, here we started already with electron. Okay, here will be gamma Bremsstrahlung radiation, that means gamma, again pair production, again Bremsstrahlung radiation, and okay, you have any process will produce two. Yeah? That means we obtain geometrical cascade. Okay, this deepness of this your electromagnetic shower, it's possible to express in nature units, which in this case will be this radiation length. Okay, that means okay, we have Also very important quantity is critical energy. That means that in this case, if energy is higher than this critical energy, in this case, this radiation losses starts to dominate over ionization. For higher energy, you have domination of radiation losses. For lower energy, you have domination of ionization. Yeah. Okay. This is for this critical energy and radiation length. You have relation for this ionization losses. And again, this energy is possible to show in a natural unit, which will be, in our case, this critical energy. And okay, as I said, any process will produce two particles. Yeah, that means on the end, you will have so many particles, yeah, which will be this given by this critical energy. Because, okay, after critical energy, this will not be production of new particles, because will be not this. This will be ionization, no Bremsstrahlung radiation, and also for approximately this energy, this Compton scattering and photo effect will dominate on the pair production. That means it's possible to calculate how many particles you will have. And also it's possible to calculate how will be this thickness and how many particles you will obtain. And here is example for lead and energy about 3 GeV in lead. In this case, this maximum of this electromagnetic shower will be in this unit of radiation length 6, and the number of this particle will be about 400. This electromagnetic calorimeters, which we described, these walls of scintillation detectors, are given by segmented detectors with long crystal, which have this length, which is more than 15 radiation lengths. And okay, that also this radiuses should be near this Molière radiuses. And whole energy we will obtain a sum of energies from main and also surrounding modules. Yeah. What is lost, this problem is that some energy we will lose from these modules, which have very small contribution of energy, and that this is some threshold. Yeah, and this contribution will be smaller than this threshold. Here, this position of center, that means we need to have also to know direction from which this gamma was running. And in this case, it's possible to use this position of center and determine as weighted value of this coordinates. The best, maybe not the best, but usual weight is given by energy in these modules. But in principle, other types of weights it's possible to use also. Here it is example of one of such spectrometer. This is this two-arm photon spectrometer, which is based on barium fluoride spectrometer. This thickness length of this crystal is in this case about 250 millimeters, and diameter is about, because okay, it is not circular, but it is hexagonal, and it is between 50, this inside diameter is 54 and outside is 59. Yeah. This radiation length is about 20 millimeters. That means, okay, it is more than 10 times radiation length. And this molar radius is about 33. That means diameter in this case is 68. That means it's fine. Critical energy is 12.7 MeV. Yeah. And here there are examples how is this resolution of energy resolution for energy of gamma about 160 MeV. If you have only one detector, it is about 16%, but if you will use this all detectors which are hit by this electromagnetic shower, it is about 60%. For higher energy, it's about 3%. Here is dependency of this resolution on energy. Yeah. Okay, very oftenly these electromagnetic showers are used for detection of high energy photons which are produced from decay of neutral particles. Okay, my question. If you said that you have this special theory of relativity lecture some, do you know how is possible to obtain invariant mass using invariant mass of particle which is decaying to another particles? How is possible to obtain this invariant mass? Do you know?
No, I don't know.
Okay, fine. I think that at Thursday I will prepare for you how it is possible to do. Yeah. And we will before start of our lecture we will discuss this, as we already discussed this Bohr model. I will show you how it is working. Yeah, here is
Okay.
only result. Yeah, and result which is valid for a decay of particle to 2 photons. Yeah, in this case it's enough to know energies of these 2 photons and angle between these 2 photons, and you will obtain mass of particle which was decaying to these 2 photons. Yeah, that means we will obtain this particle invariant mass, and it is possible also to obtain uncertainty of this invariant mass. Do you know how it is by this Taylor expansion, and how it is working? It's possible to work with these uncertainties of experimental.
I don't know.
Okay, fine. That means it will be necessary to show you also this, and we will make some exercises with this. Yeah. Okay, that here is some results which were obtained, some spectra which were obtained from this from this electromagnetic calorimeter. And there are very important feature which made possible to distinguish between this gamma and another particles. Yeah. This charged particle is no problem to distinguish. You will put before this scintillation detector for gamma, you will put some very thin plastic scintillator which detect this charged particle, and you will distinguish between charge and neutral. But neutral particle, it's photons, but it is also possible to have neutrons. And neutrons and photons is possible to distinguish by time of flight. Yeah, here is timing. Yeah, it is time of flight of different particles. And you see that here you have some maximum peak, which is given by photons, because all photons are running with the velocity of the light. Yeah. And okay, and here there are neutrons because they will come later. Yeah, because this is timing, this is in nanoseconds, and okay, this is distance was about, I think it was about 4.3 meters. If you will calculate this time for photons, you will obtain some nanoseconds, and you will obtain that you will have peak here. Yeah, and here there are these neutrons, and from because if you will measure this time, it is possible to calculate velocity, and from velocity of neutron, it's possible to calculate energy of kinetic energy of neutron. And here is possible to see that it's possible to distinguish neutrons up to energies on about 1 GeV. Yeah, it is low energy 0.1 GeV, and here is high energy neutrons. Also, it's possible to distinguish these photons and neutrons from mean multiplicity. From multiplicity, how many modules were covered by shower. Because this electromagnetic shower, which is produced by photons, is different from hadronic shower, which is produced by neutrons. Yeah? That means from this comparison, it's also possible to distinguish these two. Okay, fine. For today, it is all.